Welcome to the fifth video on Introduction to Constraint Logic Programming through Picat. This will be the last video in the series. The topic of this video is constraint solving. Many tasks involve combinatorial search, and any combinatorial search problem can be formulated as a constraint satisfaction problem, CSP in short. A CSP consists of a set of variables, each of which has a domain, and a set of constraints among the variables, and optionally, an objective function. A solution to a CSP is a valuation of variables that satisfies all the constraints and optimizes the objective function if it exists. So let's take a look at this toy problem, a crypt arithmetic puzzle. Send plus more equals money. So given the digits, given the letters, we want to assign each digit a unique, each letter a unique digit, such that the equation holds. Send plus more equals money. All right, let's write a program in Picat to solve this problem. All right, the first thing you need to do is you need to import a module. Okay, there are four constraint modules in Picat. All right, let's import CP. All right, so you need to generate the variables. Okay, in this case, you need to have a CSP model. Okay, in this case, okay, the model is quite obvious. So what do? We use a variable for each letter. All right, so let's say vs, okay, equals s. Send more, okay, y. Okay, these are the letters. And then we need to declare the domain. Okay, declare the domain for each of the variables. So this is 0 to 9. And then we need to write the constraints. Okay, so of course, send as a 4-digit integer. The leading digit cannot be 0. Okay, so s not equal 0. All right. So this is a built-in. Okay. So this not equal is a built-in. Okay. This means not unifiable. Okay. This is a built-in used for terms. Okay. For constraints. Okay. So we use this operator. Okay. Sharp and then this not equal symbol. And also same to the more. Okay. M is a leading digit. It cannot be 0. And then we write the equation. Okay, send plus and all the digits. Okay, all the digits are different. All right, so we use this global constraint or different. So vs. Okay, and then we write the equation. Okay, send. Okay, as a weighted sum. Send has a power. Okay, it is 1000. Okay, so 1000 times s plus times e and times n and times d. Okay, so this is a send plus more m o and r more and equals money. All right, so equals, again, this equality This is for constraint. Okay, so this is sharp equal. Okay, means equality constraint. All right, equals the money. All right, so this is 10,000 and money and money. And E and money Y. Okay, so this is the constraint, right? So, and then, okay, the last thing after generating the constraints, okay, we want to label the variables with the values, okay, by using this built-in, so VS, and then we output, okay, output the values. Okay, let's just print, right? All right, so okay, send plus more equals money. All right, so now, okay, we can run the program. So let's say send more. Okay, it's good. Okay, we send it wrong. All right, so this is a solution. Yeah, this is a solution. Okay, so okay, there are several modules in case you want to use a different solver. Okay, instead of using CP solver, okay, you can use set. Okay, set solver. Okay, the set solver. There is a set compiler, which compiles all the constraints, okay, to conjunctive normal form, and then it calls a set solver to solve it. And you can also use this one called MIP. Okay, mixed integer programming solver. This MIP solver, okay, actually supports not only integer variables, but also real values. MIP solver, in order to use a MIP solver, you need to install MIP solver. Okay, so actually in my computer, I have two MIP solvers installed, the Groovy solver and also the CBC solver. All right, you can also use SMT. Okay, this is SMT solver. It has a connection to Z3 and the CV4 solvers. Okay, but I have to say, for finite domain constraints, okay, SMT solvers are not so competitive. Okay. All right, good. So that's our first example. All right, the next example I want to show you is, okay, you know, every called a satisfiability problem. Okay, I have this problem set .py. All right, so the satisfiability problem is, okay, giving a set of variables and a Boolean formula. Okay, and the problem amounts to finding a check if the formula is satisfiable or not. And if it is satisfiable, okay, then find a solution. Okay, find a solution assignment, okay, for the variables. So this is one example of the satisfiability problem. So in this example, there are 4 variables, and all the variables are Boolean. Okay, Boolean variables are treated as integer variables, 0, 1 integer variables. And then, okay, there are these operators. Okay, you see these, okay, operators. This is for implication, and then this is for logic OR. This is for negation, and this is for equivalence. Okay, this is for, okay, logic AND. Okay, so this is a formula, and then it uses solve. Okay, and then print out the value. All right, let's take a look at another. This is okay, the very first problem that was found to be an NP complete problem. All right, so let's take a look at another problem called maximum click problem. So this is a click. All right, so give me a graph. Okay, so in our case, a graph is represented as an adjacency matrix. Okay, so the entry is 1 if there is an edge. Okay, let's say vertex 1 to vertex 2, there is an edge. Yeah, and the entry is 0, okay, if the two vertices are not connected. All right, so what do we do? Again, so we use set solver. Basically, for this type of problems, set solver is the most competitive. All right, so for 0-1 integer programming problems, okay, the set solver is the fastest. So, okay, we get the graph. Okay, so this is the number of vertices in the graph. And then we create a list of variables. Basically, for each vertex, we create one variable. And all the variables are Boolean. Okay, so that means there are 0-1 integer variables. And then we use this for each. For each, this is like a loop. Okay, it takes iterators and conditions. Okay, in this example, there were 2 iterators. Okay, so u okay is over this range, and v is in this range. Basically, okay, this for each iterates over all pairs. Okay, all pairs of vertices. Okay, so this graph is undirected. Okay, so assume it is undirected. So all possible pairs. So if the vertex, this vertex u is in a click, okay, that means the variable, this vars u is 1. And also vertex v is in a click, all right, this is 1. Okay, then, okay, this u and v must be connected. Okay, then that means the entry guv must be 1. Okay, and this is the optimization problem. Okay, we want to find a maximum click. Okay, so we want to find an assignment that maximizes this total sum. All right, so this is another example. Okay, next, let's consider another famous NP-complete problem called a vertex cover problem. Again, okay, give me a graph. Okay, we want to find a set of vertices that covers all the edges in a graph. Okay, so it is very similar to the previous maximum click problem. So for each vertex, we use a variable. Okay, it is 0-1. Good. And then for each pair of vertices, okay, so what do we do? If this pair has an edge, yeah, if it has an edge, then this edge must be covered. Okay, that means either, okay, u is in the set, okay, or v is in the set. Okay, we want to find a minimum set, okay, that covers the graph. Okay, so we want to minimize, okay, the sum of the variables. Okay, so that is a vertex cover problem. All right, next one is called a Hamilton cycle problem, HCP. So give me a graph. Okay, this one is say, a directed graph. Okay, giving a directed graph, we want to find a Hamilton cycle, okay, in the graph. So first, okay, how to represent a directed graph. Okay, we use domain variables to represent a graph. All right, so basically for each vertex, okay, we have a variable. We have a variable. This is like an adjacent list representation of a graph. So v1, so that means from vertex 1, okay, there is an edge. Okay, 1, 2 is an edge, 1, 5 is an edge, okay, 1, 6 is an edge. So this is this domain variables represent the given graph. Okay, and there is a built-in constraint called a circuit. Okay, this one is true if the assignment forms a Hamilton cycle. All right, so we just use this. All right, so this modeling is easy, and then we find find a Hamilton cycle problem. Find a Hamilton cycle and print it out. All right, next problem is called SubsetSum problem. Okay, SubsetSum. It is another well-known NP-complete problem. Okay, giving a set of integers. Okay, let's say this is a set of integers. Okay, and a target number. Okay, what do we want to do? Okay, we want to find a subset. Okay, find a subset whose sum equals the target number. Okay, so this basically this modeling for each number. Okay, we use a Boolean variable. Okay, if the variable is 1, okay, that means the number is in the set. All right, otherwise, okay, it is not in the set. And we use this constraint, okay, to say, okay, there's b times the element. Okay, we use a zip. Okay, so basically, for each variable and each integer. All right, so each variable and an integer. Okay, so what do we do? Okay, for each pair in the zipped list. Okay, so we add this term. Okay, add this term, and the total. Okay, the total equals the target. Okay, and in this example, all right, we use the MIP solver. Okay, actually for this type of small problems, it doesn't make much difference. Okay, which solver you use doesn't make much difference. Okay, so in my computer, the CBC MIP solver is installed, and then you can tell the system or use CBC solver, okay, as a solver option. Okay, this is all right. Let's consider another example. Okay, called magic square. Okay, this is another famous example. Magic square. So giving a grid. Okay, in this case, it is a 4x4 grid. All right. So what do we want to do? We want to assign a unique integer to each cell. Okay, each square to each square. Okay, to assign integer from this domain to each cell, such that every row, every column, and also two of this diagonal. Okay, the primary diagonal and the secondary diagonal. Okay, all have the same sum. Okay, in this case, okay, sums to 34. Okay, 34. So, all right, we use this. So all the entries are okay. What do we do? So we have a two-dimensional array, and all the entries, okay, are variables, and the variables have this domain, okay, from 1 to 16, and all the variables are different. Good. All right, we use this vars, okay, vars to get, because all different expects a list of variables. And so what do? We use this function vars. Okay, vars takes a term and it returns a list of variables in the term. Okay, so and then we write the constraints. Okay, so for each I in this range, what do? Okay, every row, yeah, every row, okay, has this sum. Okay, so the row I has this sum and the column I has this sum. And then we write the primary diagonal, and the secondary diagonal. Okay. And in this example, we use CP. For this example, actually CP The CP solver provides several modeling, okay, we call labeling strategies. All right, for this example, all right, we use this FF, called FF, first field principle. Well, basically, it selects domain, the smallest domain first, okay, and then prints out the value. Okay, so we could run this. All right, you can see the difference. Okay, you can see magic square. Okay, and also let's measure the time. All right, well, actually, it is pretty faster. Okay, the CP solver is pretty faster. Okay, you can change it to square. I think this is not hot enough. All right, so the problem is still a toy problem. Okay, so okay, now we use set solver. Okay, use set solver. And let's see the time. Well, it takes a little bit longer. Okay, why? Because set solvers are normally not good at handling numbers. Okay. But this one is okay. Okay, in general, set solvers actually I have found that the set solver outperforms the CP solver. Okay, in general case. So if you have time, okay, unless unless the time limit is really small, all right, the CP solver, or the problem is really small, or you have some problem specific labeling strategies. Okay, otherwise the set solver, okay, is pretty efficient. All right, the next example is called a Sudoku puzzle. Okay, Sudoku, that's a very famous puzzle. A lot of people play it, called Sudoku. So this one, giving a grade, again, giving a grade. Okay, so in this case, it depends on the size of the grid. Okay, let's say this is 25 by 25 grid. Okay, so what do we want to do? We want to assign the numbers, numbers from 1 to 25, okay, to the cells, okay, such that every row has different numbers, every column has different numbers, and also every small square. Okay, this is a small square. In this case, every 5 by 5. Okay, every 5 by 5 small squares also has different numbers. Okay, so and modeling. Okay, what do we do? Okay, we first fetch this array. Okay, this is a grid. All right, basically there are pre-filled entries, and the underscores are blanks. Okay, these are the blanks, and the solver will fill in the blanks. So the domain of the variables is from 1 to n, and then we write the constraints. So for each row and okay, all the numbers in the row are different, and for each column and all the numbers in the column are different. All right, so what do we do? How to get the column? We use list comprehension to retrieve all the entries, okay, in this column. Okay, so for each row in this, and we get row column. And then we get the small square. Okay, all the small squares constrain the entries of each of the small squares. Okay, the dimension of the small square is this. Okay, so giving n. So if n is 25, then m is 5. And then we write this. Okay, for each of the small squares. Okay, basically this row column. This is the starting row number and the starting column number of each of the small square. And then we get all the entries in the small square, again using a list comprehension. And then we say, okay, all the small squares are different. And then solve. All right, this one uses a set. Actually, set is extremely efficient. Okay, for a problem like a Sudoku. Okay, so well, you see, this is 25 by 25. Okay, it's a pretty hard problem. All right, you see, this Sudoku. Again, time, measure the time. Oops, something is wrong. Oh, Sudoku. Okay, I don't think I did a good preparation. So this one is not supposed to be there. So let's run it again, Sudoku. Okay, it came out instantly. Okay. Well, you could try other solvers. So in general, for a problem, okay, normally you don't know which solver performs the best. So what do you need to do? You need to do experiment. All right. Well, since in Picat, okay, you can write the same model and experiment with different solvers. Okay, what do you need to do? You just okay, need to import a different model. Okay, so you can switch from one solver to another solver seamlessly. All right, let's consider one more problem. Okay, this is called N-Queen's problem. N-Queen's, okay, this is a very famous problem. N-Queen's, okay, so giving originally it is 8 by 8. Okay, so 8 by 8 is not interesting, computationally interesting, okay, because it's the search space is not big enough for experiment. So in general, it's n by n. Okay, so giving a n by n grid, okay, you want to put n queen pieces on the board such that, okay, no two queens attack each other. Okay, you know in chess how the queen piece moves. The queen basically combines the movement of the rook and the movement of the bishop. So a queen can move horizontally, vertically, and diagonally. Okay, so that means okay, two queens attack each other if two queens are placed in the same row, the same column, or the same diagonal. All right, so here is we have two different models for this. Okay, one is this is all right. So what do we do? Okay, for each well, let's say for each row, we use variable. Okay, we use one variable q. Is so there are n rows, so we use n variables, and all the variables. Okay, each of the variables gives a column number. Yeah, column number. So that means q1. Alright, gives a column number of the first queen, and Q2 gives a column number of the second queen, and so on. Alright, so now we need to write the constraints. Okay, no two queens are in the same column, so Qi for each pair ij, and Qi, okay, not equal, okay, Qj, okay. And also not in the same diagonal, yeah, okay, not in a diagonal that is parallel to the primary diagonal. Okay, so this one, use this constraint, and not in a diagonal that is parallel to the secondary diagonal. And then, okay, so this is the constraint, and then I use FF. Actually, for this one, the first fail principle, this FF labeling strategy works very well, and we can say, okay, time queens. All right, so by default it solves 100 queens. All right, it comes out instantly, and we can try 1,000 queens. All right, so 1,000. Wait, maybe it takes several seconds. Oh, it's still, oh, okay, so it takes 10 seconds, about 10 seconds. All right, so 1,000 queens. All right, let's consider another model. All right, this is we call Okay, in this model, so for each cell, we use a variable, a Boolean variable. Good. So the Boolean variable, if the variable is 0, that means there is no queen. Okay, put on that cell. If the variable is 1, that means okay, there is a queen. Okay, at that cell. And so then we create n by n, okay, n square variables, and all the variables are Boolean. And then we write the constraints. All right, so for each, okay, also for, of course, for this type of problems, then we should use set. All right, CP solvers, okay, in general are not good at dealing with 0, 1 variables. All right, so for we make sure, okay, each row has exactly 1 queen, okay, and each column has exactly 1 queen. Okay, and then we also okay constrain the diagonal. Okay, diagonal for these diagonals. These are all the diagonals that are parallel to the secondary. Yeah, parallel to the secondary diagonal. And for each of these diagonal, okay, we retrieve all the entries. Okay, the sum of these variables is less than or equal to 1. Yeah, and the same to the diagonals that are parallel to the primary diagonal. Okay, so and each diagonal, okay, the number of queens placed in that diagonal is less than or equal to 1. All right, good. All right, so I have shown you several examples. Okay, basically, it is this Picat has good modeling capability. Okay, because of the availability of the language constructs such as arrays, okay, loops for each loops, and list comprehensions. Okay, actually, and also there are several solvers available, so you can pick the best solver that suits your problem. All right, so I have in this video lectures, okay, I have introduced you the Picat system, okay, and I talked about the functional programming, logic programming, using pattern matching rules, and I talked about recursive programming and dynamic programming, and in this video I talked about constraint programming. Well, I don't think this is comprehensive, but I think you are ready to explore and you are ready to write programs to solve problems. And for details, okay, you can take a look at the user's guide, and you can also, okay, there is a book available published several years ago on constraint solving and planning with Picat, and that's also a good resource. And I want to point you to another source, that is Hakan Constraint's page, Picat page, and Hakan has written more than 1,000 programs, and probably, okay, when you come to a problem, okay, very likely, okay, and he has already solved it. Okay, I mean, if it's a popular problem. All right, so that is the end of this video and also the end of this series. Okay, thank you very much for watching.